This is example number 3 of section 13.4, chapter 13, right? So we have the motor wings in a cable with a constant acceleration such that the 20 kilograms crate, so we know that the mass is 20 kilograms, so we have to be clear what our data is. Crate move a distance of 6 meters, so we move a distance of 6 meters in a time of 3 seconds, starting from rest. That's important. And we want to find the tension developed in the cable. This is the cable right here. This cable, this is the motor. So we have a motor that is winging the cable right there, and that goes up. And very important, we have a rough surface. We don't have a smooth surface, so we do have friction right here. Let's work with the solution. So we have to apply our equations of motion, right? So if we have our acceleration, we will be able to find our forces, in this case the tension. But actually we are not given the acceleration either. We are given that the acceleration is a constant acceleration, and we are given the distance, and we are given the time. So in order to find our tension, which are forces, first we have to find our acceleration given the distance and time. We know that the acceleration is the second derivative of distance, therefore the distance is the double integral of the acceleration. So for constant acceleration, we know that our distance is initial distance plus initial velocity times t plus 1/2 acceleration squared, right? This equation is only valid for constant acceleration. So the crate start in 0 distance, so this is 0, and start from rest, so this is also 0. And we know that we cover 6 meters in a time of 3 seconds. We can calculate our acceleration, and if we solve for the acceleration, we get an acceleration of 1.33 meters over second squared. So now we have the acceleration. Now if we have that part of the equation, right, we can find that part of the equation. So the next step is to do our free body diagrams and our acceleration diagrams, which are called kinetic diagrams. So let's do our free body diagram. So we draw our system in this direction. As you see, we always have to choose first our coordinate system, since we are in an inclined surface and all the motion occurs in that inclined motion. I will choose, rather to choose an horizontal and vertical coordinate system, I will choose an inclined coordinate system, x and y, and that system is inclined 30 degrees because everything is happening in that direction. So my free body diagram, what does it have? First, the weight. Even though I'm using an inclined system, the gravity always goes vertical. I cannot draw the gravity in any other direction, and even if I've inclined the system, I have to still draw my gravity or my weight in the vertical direction. So this is the weight. And as we know, the weight will be mass times gravity, which is 20 times 9.81. Then I have a normal. The normal force is an unknown, and I do not know where is that located, not necessarily in the middle of my body. And then the body moves upwards, so I have a friction force that opposes that motion. So my friction force will always be in the opposite direction of the motion. So I'm moving in that direction, so my friction force will be in that direction. Besides that, I have the tension that I want to find. So I have actually several unknowns that are my friction, normal, and tension. And then I can draw my kinetic diagram. My kinetic diagram will be in the same direction. And this is, I'm not going to be moving in the y direction, I'm going to be moving only in the x direction. So my kinetic diagrams will be M, A, and since this is my new x, I will draw, that's x. So those are my two diagrams, and as I know, I will make them equal. Let me write my equal sign like that. So those are equal because external forces are equal to mass times acceleration. So equation in x direction, I will have tension and friction equals to my mass and ax. But I noticed that the friction will have to be related, when I'm already moving, it has to be related to the normal. I know that the friction is my coefficient of friction times the normal. I know the coefficient of friction is 0.3, but I do not know the normal. So let's first add forces in y direction to find how much is that normal. So I find my forces in y, and in y I have, if this vector is vertical, you see that this angle here is also 30 degrees. So this here is 30 degrees. So if I'm adding forces in the y direction, I have the weight times cosine of 30 degrees in the negative direction of y plus the normal direction that is perpendicular to my surface, so it is in the y direction, so I don't have to multiply for any angle. And that's equals to, it has to be equals to the mass times acceleration in the y direction, but since I'm not moving perpendicular to the surface, this is equals to 0. So my normal is equals to weight cosine of 30. And this is equals to 20 times 9.81. And cosine of 30, you know that is square root of 3 over 2. So the normal is equals to 169.9 newtons. So I have my normal force calculated that I will use mainly. I will use that normal force mainly to calculate my friction force. Okay, now I add forces in my x direction, and I have the tension, right, minus the friction force, minus a component of the weight, which is that one right here, minus weight sine of 30, right? And the normal does not participate, equals mass AX. The tension is what I want to find, so let's solve for tension already. Tension is equals to mass AX plus the weight times sine of 30, which you know that is 1/2, plus the friction, which is 0.3 times the normal, which already I calculated. Let me write it here, 169 times 9. So I can solve for the tension. The tension then will be equals to mass, the mass that is 20, the acceleration that I already found right here, 1.33. Actually, this is a periodic. I could actually write to be more accurate. It's very important that you don't carry over rounding errors all along. I mean, I only write two significant figures, but you can actually write in your calculator as many significant figures as you want. This is a periodic number, so it's 1.333333 plus the weight, which is 20 times 9.81, half of that, plus 0.3, 1.699. Actually, 169.9. And then we solve for the tension, and the tension is equals to 166 newtons. Okay, so that's, let me write that result somewhere else, because here maybe you don't see it. So we got the acceleration and the tension. The final result for the tension was 166 newtons, which we were asked to calculate. So the tension developing the cable is 166 newtons. What did we do? Just to review, we were given distance and time and a constant acceleration, so we were able to find that constant acceleration. And then we did our free body diagram, our kinetic diagram, and make them equal at forces in x and forces in y. And then we were able to find forces when we have acceleration.